Ever stop to think how a single, tiny seed can contain all the information needed to grow a massive oak tree? It's mind-boggling, right?
It really is.
So what if the universe itself works on a similar principle, encoding its seemingly infinite complexity within finite boundaries?
Like those patterns in a kaleidoscope.
Yeah,
Squeezed into a small space.
exactly.
That's a beautiful way to frame it, actually. And it really touches on some cutting-edge ideas in theoretical physics, particularly this concept of the inverted island being explored by researchers like Langhoff, Murdia, and Nomura.
I've heard about that work.
Their work suggests that the sheer vastness of the multiverse might not be as informationally overwhelming as it seems. There could be a kind of computational redundancy, where all the essential information boils down to what's encoded on a finite boundary. It's a truly revolutionary perspective.
It really flips how we think about things. It immediately brought to mind something we dug into episode 16.
What was that?
We explored how prime numbers, those fundamental building blocks of arithmetic, can create these incredibly strange geometric shapes. Fractals.
Fractals, of course.
These things can have zero length, like a single point stretched out infinitely, almost. Yet somehow they still possess a full dimension.
Despite being infinitely sparse. Yeah, mathematically fascinating stuff.
Felt like pure mathematical wizardry.
But now you're seeing a potential echo, aren't you?
A surprising harmony between these abstract math ideas and
the latest thinking about cosmology and quantum gravity.
Exactly.
It's often in these unexpected intersections, isn't it?
Absolutely, where the really profound insights emerge. And that's precisely what we're diving into today. Our mission really is to explore this potential connection. How these concepts from pure math, specifically involving primes and fractals, might give us a new lens, a new way to understand the fundamental nature of the multiverse.
And how information is handled in quantum gravity. It's a big one.
It is. So get ready, because this is where things get really interesting. Hopefully some genuine aha moments along the way for everyone listening.
Looking forward to it.
Okay, let's try to unpack this central idea that keeps popping up, both in our past chat about prime fractals and this inverted island thing. It's how you can have something that seems infinitely complex, but ultimately it's described by a finite boundary that holds all the crucial information.
It's like the universe and mathematics are both masters of information compression. That's a fantastic analogy.
So think about the multiverse with eternal inflation. This picture of an infinitely expanding spacetime. It's huge, maybe infinite.
But the argument behind the inverted island is that a lot of that infinite information is actually, well, redundant for describing the physics we observe.
In the work, these interactions, like collisions between expanding bubble universes and collapsing ADS bubbles, act as a natural cutoff, creating a kind of boundary.
And this leads to the idea of an entanglement island, a finite region in space.
And it's identified by something called the quantum extremal surface prescription.
Think of it like the universe drawing a border around the most important information, a cosmic best of selection. Quantum extremal surface, or QES, is crucial. It essentially picks out a finite region of spacetime that holographically encodes all the information from beyond it.
Holographically, even though the multiverse appears infinitely vast.
The key information needed to understand its semi-classical physics, the physics we need for making cosmological predictions, resides within this finite island.
It's like the universe is incredibly efficient at storing information.
Or maybe just showing what's actually relevant.
Brings us back to those mind-bending prime number fractals we talked about before.
The DPCS and related sets.
We saw how even by meticulously removing an infinite number of points or intervals based on the distribution of prime numbers.
Like the Cantor set construction with primes guiding the cuts.
Exactly. You can still end up with a finite fractal island. It could be a set with zero length yet filling a whole dimension, or even a fat fractal that keeps a chunk of its size.
It's like you're taking away almost everything, but the essential structure, the identity shaped by the primes, still remains within that finite remnant.
Yeah. That's the key parallel, isn't it?
These fractal sets, even after seemingly losing so much through this prime-based removal process, still retain their core characteristics.
The fingerprint, you called it.
Yeah, the specific way the primes are distributed and used in their construction leaves a unique fingerprint. It's almost as if they continue to encode the entire sequence of primes within that finite structure.
Like the ghost of the full prime sequence still haunts the fractal. That's a great way to put it. You have this seemingly infinite spacetime in the multiverse that self-compresses into a finite island holding the essential info.
Right, through the QES prescription.
And then you have these abstract mathematical sets where even after deleting infinitely many parts, a finite fractal island can still carry the full essence of its dimensionality.
The mathematics governing this prime-based removal and the resulting dimension, it seems to echo this quantum extremization process that selects these finite informational islands in cosmology.
It's a less is more scenario.
It truly is a potentially profound connection. You demonstrated how these measure zero but dimension one fractals, born from the seemingly random primes, possess this incredible informational density. And the inverted island research shows how area-divergent but entropy-finite entanglement islands can arise in quantum gravity.
So we arrived at this idea of a finite region in infinite complexity using fundamentally different toolkits.
Absolutely. They constructed their island using space-time and quantum mechanics.
And we constructed ours using number theory and fractal geometry.
This is where it gets really mind-blowing, as your team's notes highlight.
Yeah.
This unexpected mirroring between Cantor prime fractals and quantum islands could have significant implications for theoretical physicists.
They might not expect these unrelated areas to align so cleanly.
When you start to examine the underlying mathematical structure, the connection becomes even more compelling.
How?
Both stories, despite their different settings, cosmology versus number theory, can be understood through the lens of extremization problems.
Extremization problems, like finding a minimum or maximum value.
Finding the minimum or maximum value of a certain quantity.
How can we see both prime fractals and entanglement islands coming from a similar math approach?
Okay, let's first think about how we determine the fractal dimension of something like the dynamic prime Cantor set, the DPCS.
Right, the Hausdorff dimension, D.
That dimension D is found by solving an equation. You sum over all prime numbers with a factor involving raised to the power of D, and this whole sum has to equal 1. Remember that.
Yeah, the Moran equation, essentially, sum equals 1.
Now, imagine we define a function, let's call it mathfrac, as that sum minus 1.
The function is 0 when the sum equals 1.
Finding the dimension where the sum equals 1 is the same as finding a D where this function becomes 0. It's also where its rate of change with respect to D is also 0. That second condition, the zero rate of change, that's the extremization part.
Finding a point where the function is flat, like a minimum or maximum.
Exactly, a stable point. So the fractal dimension is this value that makes this mathematical function stable, reaching an extreme point.
Okay, I'm following that. Now, how does this connect to entanglement islands in the universe?
In the case of entanglement islands, the rule involves minimizing something called the generalized entropy.
The island rule.
The amount of quantum information in some region is related to minimizing this generalized entropy combined with some possible island, and you minimize it across all possible choices of that island.
This generalized entropy has different parts.
Yes, it has a part related to gravity, basically the area or size of the boundary of the island, and apart from quantum field theory, which is the amount of quantum entanglement entropy within an island.
Right, makes sense.
So if we define another function, let's call it island I, as this generalized entropy minus some target value, then the true island is the one that makes the change in this function equal to 0 when you vary the island.
Again, an extremization problem.
We're finding the island that minimizes this generalized entropy function.
Wow, I'm really starting to see a pattern here. Both scenarios involve finding a kind of sweet spot by making some quantity reach a minimum or a stable point.
Whether it's that mathematical function for the fractal or the generalized entropy for the island.
Yes. It's like both math and the universe are looking for the most stable or efficient configuration.
This leads to a profound implication, potentially.
Which is?
That primes might not just be random arithmetic noise. Instead, their distribution could be fundamental to the scaffolding through which information is encoded in a compressed form.
Both in abstract math and in the fabric of spacetime.
That's the idea. These Cantor fractals could be seen as space-like counterparts or cousins to these quantum islands in cosmology.
That's a huge leap. These abstract mathematical things aren't just curiosities.
They might be offering us a fundamental insight into how the universe itself stores and processes information. That's the mind-bending possibility we're looking at here. And this connection through the shared principle of extremization, it might be the very first bridge linking the Hausdorff fractal dimension.
That weird measure of how a fractal fills space.
In a page.
The page curve describes how black hole entropy evolves when it evaporates. That's central to the information paradox puzzle.
A key puzzle in understanding information loss, or lack thereof, in quantum gravity is that the collapse of black holes' entropy, as described by the Page curve, might have a mathematical cousin in the way a fractal dimension emerges from this iterative prime removal.
Okay, let's nail this down. We're seeing this recurring theme: infinite complexity leading to a finite island through variational stability.
This idea that by finding a stable point through this process of extremization, you can extract a finite, information-rich structure from something that seems infinitely complex, or at least vastly complex.
And if you delve deeper, you mentioned we can start to sketch out a kind of dictionary between these two worlds, primes and islands.
For instance, the removal of points or intervals based on primes in the fractal construction, the operations that shrink the set, those might be analogous to the gravitational term in the island entropy, the area term, which also tends to shrink the region of relevant information by favoring smaller boundaries.
Okay, interesting. What else?
The Moran sum in fractal theory, the thing that equals 1 at the Hausdorff dimension, could correspond to the generalized entropy itself.
The quantity being extremized.
And the conditions for finding the fractal dimension and the quantum extremal surface both arise from the same principle of variational stability, finding where a certain function is extremized.
And what about that weird property of the prime fractals, the infinite product that can give 0 length but full dimension?
That infinite product structure might mirror how the QES can result in a finite island that captures all the essential information, even from an apparently infinite region of spacetime.
It's this consistent pattern, infinite complexity condensing down to finite emergent structure, always through some form of extremization or stability principle.
And it's worth noting, this principle of infinite complexity, finite emergence isn't just limited to these two examples, fascinating as they are.
Where do we see it?
Think about the renormalization group in physics.
Zoom out over microscopic details.
You average over infinitely many microscopic details to arrive at finite macroscopic laws that work at larger scales. It's a similar idea, extracting a finite description from underlying complexity.
I see the parallel.
And then there's the holographic principle more broadly, SCFT correspondence,
where a higher dimensional volume can be encoded on a lower dimensional boundary.
Exactly. And even within holography, things like fractal screens have been explored, pointing again to this idea of complex information structures arising on finite boundaries, sometimes with fractal-like properties.
It's mind-boggling to think that something as seemingly abstract as the distribution of prime numbers could have such deep connections
to our understanding of the universe.
If primes, through these abstract mathematical rules, can generate structures that seem to mirror how the universe might encode its vastness, it really makes you wonder what other hidden languages mathematics might be speaking about the nature of reality.
It certainly does. Consider that measure zero set, the dynamic prime Cantor set, possessing the dimension of a line.
0 length dimension, still baffling.
It's a paradox in many ways, isn't it? It resonates so strongly with this idea of finite islands encoding infinite universes.
Imagine a multiverse out there, constantly spawning new universes. And what if the keys, the secrets to understanding this mind-boggling infinity, were hidden? Maybe inside finite, almost self-contained islands.
That's a truly radical shift in perspective, isn't it? Going from just one universe, even a huge one, to this concept of an eternally inflating multiverse. And it really starts with an idea from the very early moments after the Big Bang. It's called false vacuum inflation.
False vacuum inflation. Let's unpack that a bit. My understanding is it's like a period when the universe was really young, stuck in this high-energy, unstable state.
Exactly.
Supercooled water is the analogy I've heard. It's just waiting for a tiny nudge to freeze.
That's a great analogy. And this unstable state, this false vacuum, drove this absolutely insane rate of expansion in the early universe. Exponential growth.
Wow.
And here's the crucial part, the eternal bit. Even as some regions of this false vacuum decayed into a lower energy state, that's what we think formed our own bubble universe with the physics we know. Other regions just kept on inflating exponentially, like a runaway process.
It's like a cosmic chain reaction, making new bubbles, maybe forever.
That's the picture, a sort of cosmic foam constantly creating new bubble universes within this internally expanding false vacuum background.
Wild image, bubbles popping into existence.
It really is. Each of these bubbles could theoretically have vastly different properties.
Different how?
Different fundamental particles, or different strengths for the forces like gravity or electromagnetism, maybe even different numbers of dimensions.
Whoa.
It paints this picture of cosmic diversity that's almost impossible to really grasp.
Okay, but here's where my brain starts to hurt a bit. We're used to thinking about our universe, measuring things, understanding it. But when you talk about an infinite multiverse, infinite volume, maybe infinite variations, how do you even start to make sense of that? Our usual tools, our math, it seems like they just break down.
You've hit a core problem, the measure problem, it's often called.
Measure problem.
When you're dealing with infinities like this, normal ideas about probability, about making predictions, get incredibly murky.
Yeah.
How do you compare the chances of different things happening when there's an infinite amount of everything?
It's like asking, what's the probability of picking a specific grain of sand from an infinite beach?
Exactly. This leads to some really unsettling paradoxes, doesn't it?
Yeah, the one that always gets me, the one that feels just deeply weird, is the Boltzmann brain problem.
Yeah.
That comes out of this infinity.
It's a direct consequence. In an infinite universe or multiverse operating over infinite time, even the most incredibly improbable events, they're not just possible, they will happen.
Okay.
And not just once, but an infinite number of times, including the spontaneous random formation of fully formed brains, just poof, out of the quantum fluctuations, complete with memories, consciousness, maybe the illusion of a past.
So you're saying in this infinite multiverse picture, these Boltzmann brains, these flashes of consciousness, could end up being more common than brains like ours, that evolved over billions of years in a structured universe.
If you take the infinities at face value, yes, that's the paradox. However improbable the event, infinity multiplied by any tiny probability is still infinity. So these random observers could, in theory, vastly outnumber normal observers like us.
That just sounds absurd. It feels wrong. It's like, why do we find ourselves here in what seems like a normal, ordered universe if the random ones are more likely?
That is precisely the crisis. It's deeply counterintuitive. It makes us question our own existence, our observations. If the theory predicts we should most likely be a Boltzmann brain, but we're clearly not, something's got to give, right?
Something's broken with that picture, or at least our understanding of
No,
it.
either the eternally inflating multiverse idea is wrong, or our way of calculating probabilities within it, our measure is flawed. We're not correctly handling the infinities.
Okay, so huge challenge. We have this compelling theoretical idea of the multiverse coming from inflation, but trying to use our standard science tools leads to these infinite results and these bizarre philosophical nightmares like Boltzmann brain.
Exactly.
Really forces the question, is there any way to get a sensible, meaningful, maybe finite description out of this apparent cosmic chaos? How can we possibly hope to understand something infinite?
That's the absolute central question driving a lot of current research in cosmology and fundamental physics. Can we tame these infinities? Can we find a framework, a measure that lets us make sensible predictions?
It feels like we need a totally new approach. Maybe our tools are just wrong for the job.
We might need a different kind of tool. It's like trying to measure the quantum world with classical rulers. It just doesn't work. We need something fundamentally different.
So where do we look for these new tools?
Some of the most exciting ideas are coming from quantum gravity. The search for a theory that unifies Einstein's general relativity, our theory of space-time and gravity, with quantum mechanics, the theory of the very small.
Okay, the theory of everything.
Theory of quantum gravity. Because gravity shapes the large-scale structure, and quantum mechanics governs the fluctuations and maybe the bubble formation. Bringing them together seems essential.
A new concept from quantum gravity.
I am, yes. We're going to need to talk about something called quantum extremal surfaces. QES for short.
Quantum extremal surface.
It is a bit, but the core idea is powerful. They're these mathematical surfaces that pop up when you think carefully about quantum information and gravity, particularly in relation to black holes.
Black holes, how do they connect to the multiverse?
The tools developed for understanding black hole information paradoxes, things like the island rule, which involve these quantum extremal surfaces, they seem to offer a new way to think about defining regions and information content, even in these vast cosmological settings.
So QES are like special boundaries.
In a sense, yes. They're surfaces that extremize something called the generalized entropy. That includes both the area of the surface, like the Bekenstein-Hawking entropy, and the entanglement entropy of quantum fields across it.
Okay, entanglement entropy, the quantum connection.
Exactly. These QES helps identify what parts of a system are truly fundamental or what information is accessible to a given observer or region. It helps resolve paradoxes by essentially telling you where the relevant information actually is.
You think this might apply to the multiverse?
Maybe these surfaces can help us deal with the infinities. Perhaps they can lead to the emergence of these things called inverted islands.
Inverted islands. That earlier sounds intriguing.
The idea is that, counterintuitively, an entanglement island, a region whose quantum information is encoded elsewhere, might actually surround a large region inside our bubble universe. The island is the outside, the exterior.
Okay, so the island isn't in here, it's out there.
It arises because of the interactions and eventual collisions our bubble might have with other surrounding bubbles, especially ones that collapse.
Collapsing bubbles, like anti-de Sitter bubbles.
Many bubble types, particularly these Area bubbles, aren't stable forever. They tend to collapse into a big crunch singularity.
Which just sounds like an end.
Maybe. Or maybe those singularities are signals that our description, our global space-time picture of everything, is actually redundant. It's an over-description.
Like, we're counting things that aren't distinct.
The idea, motivated partly by holography, is that the true fundamental degrees of freedom might be fewer than the global picture suggests.
Okay, so back to the inverted islands and QES. How do they help with the measure problem and Boltzmann brains?
If the relevant physics, the fundamental description of our observable region and more, is actually encoded within a finite region defined by one of these quantum extremal surfaces.
Inverted island boundary.
Exactly. Then maybe we don't need to worry about the infinite volume outside. We could potentially define probabilities and make predictions just using the degrees of freedom associated with this finite region, this sort of entanglement castle, as some call it.
An entanglement castle. I like that. So you build finite walls around the part that matters using quantum gravity tools.
That's the hope. It offers a potential way to regularize the infinities, to cut off the regions that lead to paradoxes like the Boltzmann brains, and construct a well-defined probability measure for cosmology.
That sounds incredibly promising if it works out. A finite description emerging from the infinite.
It's a cutting-edge idea, very much research in progress, but it connects these deep ideas from quantum information, black holes, and holography directly to the biggest questions about the origin and structure of our cosmos.
Holography, like the universe being a hologram. We're going to zoom in.
Explore how collisions between these bubble universes, especially collisions with bubbles that are collapsing, what we call ADS bubbles, how these can lead to fundamental barriers in space-time.
Causal barriers and singularities, you mean?
Exactly, causal barriers, singularities. And this is the really surprising part. We'll see how these seemingly abstract ideas of inverted islands and quantum extremal surfaces offer a completely unexpected way to get a handle on the information within these incredibly vast regions.
Okay, inverted islands, that sounds counterintuitive.
It might feel a bit like that, like looking at a reflection that flips everything around. But honestly, that's often where the most profound insights are hiding.
Okay, so let's dive straight into it. These bubble collisions. Picture our own bubble universe, our home, just floating within this much larger, eternally expanding multiverse. It's not exactly a peaceful scene, is it?
Not at all static. These bubbles, they can, and likely do, bump into each other. And the research we're looking at, specifically a paper called The Multiverse in an Inverted Island, really highlights that collisions with these collapsing ADS bubbles are particularly important.
ADS, anti-de Sitter space bubbles, the ones with negative curvature.
That's right. And there's a diagram in that paper, figure 2. It's a Penrose diagram, a kind of space-time map, showing how our central bubble might be surrounded by these other bubbles that are shrinking instead of expanding.
Okay, so what happens inside these collapsing ADS bubbles? What's the big deal?
What's truly interesting is what happens inside them. They tend to end in what we call big crunches.
Like the Big Bang running backwards.
Everything collapses down to an incredibly dense point, a singularity. And these singularities act as fundamental causal barriers. Think of them as points beyond which nothing can ever influence us or be observed by us from the other side across the different bubble universes. It's a hard limit on how connected these different parts of the multiverse can actually be.
So these big crunch singularities sound like the universe just hitting a brick wall in that direction.
That's certainly how it looks at first glance. However, this research suggests something else. It suggests these singularities might actually be clues.
Clues to what?
Clues pointing towards redundancies in how we globally describe the entire multiverse picture.
Redundancies. We're counting things twice.
They might not be fundamental ends of space-time in the truest sense, but maybe more like indicators that our current way of trying to describe everything might be overcounting the same fundamental information.
Okay, redundancies. This idea that our standard picture, this infinitely large, constantly expanding multiverse with countless bubbles, while it feels intuitively right, might actually be a bit like an overstuffed suitcase,
That's a great analogy.
containing a lot of stuff we don't need.
Exactly. This connects directly to wanting to grasp complex topics without feeling completely overwhelmed. If our current description is redundant, it implies we're carrying around a lot of extra information that isn't essential for understanding the core physics.
So we need a more streamlined, insightful way to get the essence of the multiverse without getting lost in these potentially misleading infinities.
We need a better perspective.
So how do we find this more streamlined perspective? Is this where those quantum extremal surfaces come in?
It is a concept rooted in quantum gravity, but the basic idea behind it is surprisingly elegant. Quantum extremal surfaces, or QES for short, are essentially boundaries. Special boundaries that we identify by finding where a specific quantity called generalized entropy becomes either as large as possible or as small as possible.
Finding the peak or the valley, like you said.
Exactly like finding the peak or the valley on a landscape. We're looking for where this generalized entropy value hits an extremum.
What is this generalized entropy that we're trying to find the peak or valley of?
So generalized entropy, as laid out in equation 2 of the paper, it's a combination of two things. First, it's the area of the boundary of some region, but measured in Planck units, the fundamental scale where gravity meets quantum mechanics.
Okay, area of the boundary.
And second, it's the von Neumann entropy of the quantum fields within that region, which essentially tells us how much quantum information, or maybe quantum weirdness, is contained there.
Ah,
The formula looks like Stegen x equals a over 4gn plus Spalk x. The first part is geometry, the boundary area. The second part is the quantum information inside the boundary.
so we're adding up how much stuff is on the boundary, geometrically speaking, with how much quantum uncertainty or information is inside it.
Got it. That's the essence of generalized entropy.
These quantum extremal surfaces, by looking at this specific combo of geometry and quantum info, help us pinpoint really important boundaries in spacetime for understanding how information is organized, even in a crazy complex situation like the multiverse.
They guide us to the boundaries that are most crucial for understanding how information is encoded in a given region of spacetime, even within the vast interconnected multiverse.
Now, this leads us to what sounds like the most mind-bending part you mentioned, the inverted island. That sounds like something straight out of science fiction.
The concept of an entanglement island has been developing in various areas of quantum gravity, particularly related to black holes, but the inverted island is particularly relevant when we talk about cosmology.
How is it different from the black hole islands?
Unlike islands found within black holes, which are hidden behind the event horizon, these inverted islands actually surround a large spatial region within a bubble universe, like our own.
Wait, so it's outside in?
There's a helpful picture in the paper, Figure 1, which uses this analogy of an entanglement castle to illustrate this structure.
So instead of the island being a smaller area nestled inside a larger one, like inside a black hole, it's the other way around in this multiverse picture. The island is somehow encompassing or surrounding a huge region.
That's the key. That's the inverted part. And the paper presents what's called the island formula. It's equation 1. It looks like SR equals min x over I of Sworgen, I union R.
All right.
Let's break it down. What this formula suggests is that the fundamental microscopic entropy, the real information content, of a region we're interested in, let's call it R,
Okay.
is determined by finding another region, the island, which we call I, and we need to find the island I that minimizes the generalized entropy, that area, plus bulk entropy of the combined area of R and I together.
Okay, let me try and piece this together. We have our region R in our bubble universe. This formula tells us to look for another region, the island, which is separate from R, maybe surrounding it. We then calculate this generalized entropy for the combined zone of R and I. And the actual fundamental entropy, the info content of our original region R, is related to the smallest value we can find for that combined generalized entropy by considering all possible islands I.
You've absolutely grasped the core idea. That's it. And here's the truly remarkable discovery presented in the paper. For sufficiently large regions within bubble universes, these inverted islands actually appear. They naturally form surrounding the region R. What's even more astonishing is why they form. They arise precisely because of those inevitable collisions with collapsing ADS bubbles and their big crunch singularities we discussed earlier.
Wait a minute. So these destructive collisions, these points where space-time seems to break down, these singularities, they're actually essential for the existence of these islands that somehow encode information.
Exactly. It turns the picture on its head. They're not just cosmic train wrecks. They play a fundamental role in structuring information across the multiverse. And here's the real kicker, the truly mind-blowing implication.
Go on.
Everything we need to make predictions about our cosmos might be fully encoded in the fundamental degrees of freedom associated with just a finite spatial region, RR, and its surrounding inverted island.
A finite region encoding the infinite multiverse.
A finite, limited area containing the essential information of what could be an infinitely vast multiverse. This directly addresses that earlier point about finding a more efficient, less redundant way to understand this enormous reality.
That sounds incredibly similar to the holographic principle, the idea that information about a volume of space can be encoded on a lower dimensional boundary.
You've nailed the connection. The inverted island acts as a holographic screen for the multiverse.
But it's inside out.
Exactly. As the research points out, this is an inside-out version compared to the usual black hole scenario, where the entanglement island is found inside the black hole's event horizon. In the multiverse case, the island effectively encloses the region we're focusing on.
Okay, so those big crunch singularities we talked about earlier, instead of being the absolute end of the road, maybe they're actually hints. Hints that the information from those collapsing regions isn't truly lost, but is instead encoded somewhere else within this entanglement structure defined by the islands.
Yes, it connects back to the idea of singularities signaling redundancies in our global description.
The singularities might be telling us our initial, purely geometric picture of space-time is incomplete, that we need to factor in the quantum entanglement structure of these islands to get a more accurate and complete understanding.
It suggests geometry and entanglement are deeply intertwined in ways we're only beginning to understand.
The paper used that analogy, the entanglement castle.
Yeah.
The region R is like the central land, and the area outside, but still within some larger boundary, is like a moat.
Right.
And then the island itself, the castle, the fortress where the essential information is held safe. It's actually a really powerful image.
It is a helpful visualization, isn't it? It helps us picture this somewhat counterintuitive idea, a limited region holding the key to understanding the physics of the entire, potentially infinite multiverse.
This whole concept, hidden emergent islands, encoding way more information than we'd initially guess. It's actually sparking a memory. It really reminds me of our deep dive into prime fractals a while back, episode 16.
That's a very insightful connection to make. You're absolutely right. There are some fascinating parallels between these seemingly completely unrelated ideas. Think about it. With fractals, remember how we saw that even after removing infinite parts, based on the distribution of prime numbers, the remaining structure, the fractal itself, still held the complete information about those primes. It was all there in its intricate, self-similar pattern.
The gaps define the shape.
Exactly. And similarly, with these inverted islands, we're seeing how a finite region, by seemingly ignoring the vastness outside the island boundary, can still somehow encode the essential physics of the potentially infinite multiverse. It's like a principle of less is more operating in both scenarios.
And we also talked about redundancy back then, didn't we? With the prime fractals, how you could have these infinitely repeating patterns or self-similar structures.
We did.
That feels very similar to the idea of redundancy in the multiverse, with potentially infinite numbers of similar bubble universes.
It does track, yes. In both cases, it seems you need to focus on a specific finite subset, whether it's a particular segment of the fractal or a region R with its inverted island, to truly grasp the underlying structure and the information of the whole system.
You said the island is like a holographic screen. That mirrors how the distribution of primes, which is fundamentally a number theory thing, gets encoded in the geometric structure of the fractals. The fractal's boundary, in a loose sense, tells you about the bulk distribution of primes.
The encoding mechanism seems analogous.
And one more thing, those gaps in the fractals, the pieces that were removed based on the prime sequence, it felt like they weren't just empty spaces. They were actually key features defining the fractal's unique structure. That sounds quite a bit like how these singularities in the multiverse, these gaps in space-time, are now being viewed. Not just as flaws in our theories, but as crucial signals pointing us toward this finite encoding within the inverted islands.
The analogies are quite striking when you lay them out like that. Both the seemingly infinite realm of prime numbers and the potentially infinite expanse of the multiverse might be best understood through this lens of finite islands of information.
It really makes you wonder, doesn't it? The fractal holds its dimensional identity linked to the primes. The island holds the cosmological identity, the physics. It's like Information compression on a cosmic scale.
That's a great way to think about it. The essence is kept in this finite island, whether it's mathematical or physical. Both stories, primes, and islands are tales of holography emerging from extreme. An infinite system gets encoded onto a finite boundary or structure because that structure represents an optimal or critical point of some underlying function.
Finding the most efficient way to store information.
Or maybe it reveals a fundamental link between geometry and complexity. We see similar ideas elsewhere, too.
Like where?
The renormalization group in physics, how theories change with scale, often leading to self-similarity, like fractals. And the broader holographic principle in things like SCFT, where gravity in bulk space is dual to a quantum theory on the boundary, feels like pieces of a larger puzzle.
So wrapping this up, we started with prime fractals, these intricate mathematical objects, and ended up in the multiverse with entanglement islands. And the link is this profound idea.
That infinite complexity can be captured by finite structures, these islands, which emerge from a process of extremization. Whether it's the dimension of a fractal or the boundary of a region in space-time, something seems key.
The boundary encodes the bulk.
The non-obvious dimension of a zero-length set, or the information held by a finite island in an infinite multiverse, both point to this powerful principle.
Could these patterns in pure math, like the secrets hidden in primes, be direct reflections of how reality itself is structured?
Yeah.
From quantum foam to the entire cosmos.
And maybe our basic ideas about what size or information content even mean are insufficient when faced with these kinds of structures. Both prime fractals and inverted islands really challenge those intuitions.
Definitely a connection I wasn't expecting. Thanks for unpacking that.
My pleasure. Fascinating stuff. Until the next deep dive, keep exploring those connections.